So guys, welcome to this video, which is about building a MIDI pedal which you can use with your keyboard. And I started this little project as a quick fix, as a repair, because I have a problem with my keyboard and the sustain pedal. Now you have these sustain pedals like the one that I'm showing you here. And I'm usually connected to the input, which is on the back side of the keyboard. It's the sustain input. And then when you play a chord and you press the pedal, you are usually able to sustain the notes. I demonstrate again. But as you can see, the pedal does not work. It does not sustain the notes. Now, every keyboard player knows this problem. From time to time these pedals stop working, and usually if you take them apart and clean the contacts, you can get them back to working. You need a multimeter check for the continuity or measure the resistance. There is two types of these pedals. Some pedals are open when the pedal is depressed, so when you're not pressing it down, now it is open, the pedal. And then the switch will also be open, and when you press the pedal down, the switch will be closed. But there's also the other polarity, which is usually closed, but when you press the pedal, then it's open. So you have to check if you use the right pedal. But this is not the problem here, because there is never sustain, never any sustain. And I have to say, sometimes the pedal works. It's now, I try to demonstrate it, but I can never get it to work at this point. And now the problem is I'm touring with the band, so I need this keyboard every week. I will need it in 2 days, and I really want to use the sustain pedal because it's not a nice way of playing like this. And I feel a little bit reluctant to take the keyboard apart at this moment because I need it every week, and it takes a little bit of time sometimes to get a repair done. So I wanted to find a different solution. Okay, the first thing that I did, I have another keyboard here in the corner over there, which is a master keyboard. And I connected the MIDI out of the master keyboard to the MIDI in of my Nord Electro keyboard in order to see if I could use the sustain pedal from my master keyboard. So I wanted to know if the Nord Electro would accept MIDI commands while playing on the Nord Electro, which would then help to sustain the notes. So I could use a different keyboard to operate the sustain pedal. And I was very excited when I learned that I was able to do that. So this already showed me I have a solution. I could simply take my my master keyboard with me on stage and connect it with MIDI, and then connect the pedal to the master keyboard and then play on the Nord Electro. The only problem is the master keyboard is really heavy, so I feel a little bit reluctant to take this on tour with me unless I have to. And then I was looking into trying a different solution, which you can now see over here, and maybe you can also see that there is a little bit additional electronics on the floor. I will go a little closer so you can see. I have a microcontroller and a little board. We will look into the schematic and the code as well. And this is now connected. This is now connected via MIDI, and as you can see, I have sustain. Whenever I press the pedal here on the left side, I can sustain notes, no sustain, sustain, no problem at all, and I can use the keyboard. So here we have a look at the schematic of the Nord Electro main board, and we are interested in the sustain pedal. You can read it over here. It's written very small, but I think you can see it. And now there's only very few components that could be a cause for the failure of the sustain pedal. And as you can see, this device, the Nord Electro, is basically powered by a microcontroller. This is this large chip here, and pretty much every modern piece of electronics will be powered by a microcontroller, especially if there is a lot of functionality and displays connected, and you have rotary encoders and LEDs, it's very likely that it is powered by a microcontroller. And then you have these lines here which connect to the sustain pedal here. This line I'm particularly interested, which goes to PAI, as it is called. And if you know a little bit about microcontrollers, you pretty much understand that this is basic digital I/O what we are doing here. So we have most likely something like an internal pull-up on the microcontroller pin, and then we can short this pin to ground if we connect a pedal. And if you release the pedal, then the pin will go up to high level again due to the internal pull-up resistor. And the additional circuit that you see here is only there to protect the microcontroller. No sane person would allow to connect a microcontroller pin to the external world, because especially on stages you can have a lot of sources of electric fields, and this could easily destroy such a microcontroller. Also, in the moment when you plug in a jack, then there could be a static discharge, and so you always have to use some additional circuitry. This is here done in the form of the gates. Now these gates could also, you can also see they have an external pull-up resistor here on the input, and you would then short the input to ground with the pedal. If you have a lower impedance, here is a 10K resistor, and if you place a dead short to the ground on the input pins here, then this is a lower impedance path for the current, so then the inputs would be at 0. Which is low level, as opposed to high level, which they are due to the external pull-up resistor. So you can never connect a microcontroller pin directly to the outside world. And this is the circuitry where I would have to look for errors. So what could go wrong? So we could have a problem here with the gate. We could have a problem with the 10K resistor. It could be something like a bad solder joint. And most likely, this is my main theory, most likely we have a problem here with the phone jack itself, because I will show you what they did. They screwed the jack to the back of the case, and this could cause a problem over time. If there is the tiniest air gap between the jack and the case, when the board is installed, then the nuts that will tighten the jack to the case will put stress on the solder joints. So this is everything that we have to check. So I will probably resolder the solder joints, and then I will check the resistor and also the solder joints. And then, of course, I can also take an oscilloscope and check at the output of this gate what the signal looks like. So basically, you want to see a reaction on the output when the pedal is pressed and so here you can see what may be causing this problem. As I said, they have these nuts which screw the jacks to the case, and when they have screwed the board down before they screwed these nuts tight, then there is a very slight possibility that there is a very small, a very thin air gap between the jack and the case, which will then be, and then the jack will be pulled against the case once you tighten these nuts, and this will put a lot of stress on the solder joints. So at this point, this is a theory, but before you can repair something, you need to have a theory of what could be going wrong. So it's always good to start with a theory. Now let's look at the MIDI input circuitry, because this is what we will have to interface with, and we need to understand how this works in order to get the interface working correctly. So this is a 5-pin MIDI jack that we are going to use here, and for MIDI we only use lines 4 and 5. Now the numbering scheme is a little bit odd, because it has to do with the history of this jack. I have seen this the first time in older radios of the 50s and 60s era, but in these times they only used a 3-pin version, and they only had pin 1, pin 2 at the bottom, and pin 3 at the other side. And they would use 1 and 3 for input and output, and 2 was used for ground. Now here for the MIDI signal transfer, we only need 4 and 5. And basically we see some of the EMI filters here again. This is the same component like at the other input, so they are protecting from ESD coming into the circuit. Then we also have some protection diodes to protect from reverse current. We have a current limiting resistor here, and this device is actually an optocoupler. And an optocoupler is basically an LED, and this side here is the LED side. So we can already see that we have to get some current in. The current will be modulated with the signal. And at the output, there is a transistor circuit that will basically also be like a switch. And here you have a pull-up resistor again, and then the transistor will switch high or low following the input signal. And the optocoupler is there again to isolate the outside circuitry from the inside, and this is also part of the MIDI specification. So what we are doing here, on pin 4 of the MIDI jack, we apply a voltage. That is the 5 volt coming from our microcontroller, which is an Arduino. I will show you this in detail in a moment. And then the voltage goes through the LED, and then the current path to the ground is being switched by a transistor, which will be... So the display of the tablet went dark. So let's again look at the return path, which will go to pin 5, and then it will go to the collector of an NPN transistor, and then will switch to ground when we send a MIDI signal to the base of the transistor. So what do we need to build such a circuit? Only very few components are required to make this work. So first of all, we need a microcontroller. I have used an Arduino Nano clone. Then we need a power supply. You can use a small wall plug unit like this. And of course we need a MIDI pedal. I have soldered a jack to a cable, and then I have soldered this cable to a digital input pin of the microcontroller. I'm using pin 2 over here, and the other side of the cable connects to ground. Then the ground connection will also go to the interface circuit, and then we have pin number 1, which is also called TX. This is where we can send data. And for this project, I'm going to use a MIDI library. Now, if you know some of my videos, I sometimes talk about the pros and cons of using libraries, because I am not generally convinced that it is always the best idea to use a library. You rely on someone else's code, but in this particular case, it helps to get the project done in a very short amount of time, and also it can help to rely on code that has already been tested. If you really want to learn a little bit about how the MIDI protocol works internally, it is a little bit better if you try to write a little bit more code on your own. Now, for this project, I just wanted to get it fixed. As I said in the beginning, I want to use the keyboard in 2 days, and I will continue to use it every week in the coming weeks, so I need a working pedal. And I was only interested in finding a solution for that. Now let's look at the interface circuit. If you have the code running on your microcontroller board, the first thing that you can do is connect an oscilloscope to the output line, and you will then notice that the signal will be high in idle mode. So when you do not press the pedal, when the pedal is released, completely released, the signal will be high, and only when you press the pedal down and you send the commands, you make a Midi transmission, data transmission, then you will have very short pulses going to the low side, which will then be transferred to the keyboard and will contain the message, the Midi message that will switch the sustain pedal. And as we have seen on the keyboard side, so this is basically the keyboard side that I'm showing here, there is an optocoupler. I have used a simplified circuit. I did not write the I did not draw the EMI filter here. It's a simplified version, and I only show one part of the optocoupler. So this is only the LED part of the optocoupler. I left out the transistor part. So what we are basically, it's very simple to understand. We are switching an LED on and off in the rhythm of the message. Okay, so the message has a rhythm containing pulses, and we want to switch the LED according to the pulses. Now here is the problem. The MIDI specification implies that the LED will be lit when we send a message, but when we have a high signal coming in from this yellow cable, the yellow cable is coming from the TX, and it is high when idle and it will be low when transmitting data. So it is clear that we have to transform the polarity of the signal. And this is why we need two transistors in order to switch the LED here. If we only use this transistor, now think again, we have to provide a current loop. So we will be sending 5 volts from our interface circuit to the LED in the optocoupler. And then the return line coming from the MIDI pin will go through the transistor, and we will short to ground if we have 5 volts going to the base. Now, as I said, we have a high level, so we have the 5 volts when idle, so this would turn the transistor on always, and this is not what we want. We want the transistor to shut off, so no current path, and only when a message comes in we have to turn it on in the rhythm of the message. So we need to reverse the polarity, and this is why we have to use this PNP transistor in open collector configuration. So if we have a high signal here, this transistor will be closed, so no current can flow, no current goes to the base. And if we have a low signal here, then this will close, and then this transistor will turn on and will provide the return path. This is basically how this works, and this is what you can see here. Now this transistor here is the transistor that switches the LED in the optocoupler. Here is the base resistor, which I've drawn here, and then this is the second transistor. And that is the base resistor for the second transistor. And then I left some current limiting resistors. I have simplified the circuit a little bit. Here are some current limiting resistors, which are these two resistors in series. So that's pretty much it. And this is all you need. Now, as a last step, I want to talk a little bit about troubleshooting and how you can simplify the whole process for yourself and build it up step by step. You don't build up everything and test it and it will not work. You do some intermediate tests in between. So here we have the program code for the MIDI pedal. As you can see, it's only very few lines of program code. It's a very simple program. I like to write a little bit information for myself into the program as well. So over the time I might forget which type of pedal I have to use. Of course, you can understand this if you read through the code, but it's more work. So I always keep some information here at the beginning. So I have to connect a pedal which is open on default. On default, that means when we don't press the pedal, when it's released, it will be open contact. There will be no continuity, and only when we press the pedal we will have continuity. And I kept a note that I have to connect this to pin 2 of my Arduino. On pin 1 I have the TX. This is where we send the MIDI data, and I'm also using the internal LED, which is connected to pin 13, and I will switch this on when I detect a press of the foot pedal, and I will switch it off if I detect a release of the foot pedal. So we are using 2 libraries here. It's the Midi library by François Best, or François Best, I don't know how it's pronounced, and I'm using a library called Bounce 2. Now, if you have built projects using a microcontroller and you have used push buttons, you know that all push buttons exhibit a behavior which is called bouncing. That is, the contacts need a few milliseconds until they are really fully closed, and until this time they will behave unstable, which means they will close and then be open again, and then close and be open again. And if you have your program react on that, it can lead to unstable behavior in the program, because this bouncy behavior can be it can be a lot of bounces in very short time. So in our case, this could lead to having a lot of MIDI messages sent in a very short amount of time, which could lead to malfunction of the sustain. So you always need to use debounce. And then here also I used some define values that is only for human readability of the code. So I don't have to use pin number 2 or pin number 13, and instead of that I can use these words give a better explanation of what is happening. If I say LED pin, I know it's much clearer than writing pin number 13. Okay, here we initiate the debounce function, and in the setup we do some pin mode where we switch the input and output according to what we need. We set the debounce time to 25 milliseconds. Now, don't take too long values, because it's a musical instrument, and if your pedal has a delay of 100 milliseconds, it may be a little too long. If you take the too short time, then your pedal may not work reliably. So you have to find a balance. We start the MIDI protocol here, and then basically we're looking for 2 states inside of the main loop. So we do this continuously. We update the debounces, so we will read if the button is pressed. This is called polling. We will check continuously if the pedal has been pressed. And then we're looking for 2 states. The first one is fell, and the second one is rose. So when it fell, that means that we have pressed the button and we have detect a reliable and stable condition after 25 milliseconds stability. And then we send this MIDI message, which activates the sustain. So this is the command, this is the volume level, and this is the channel. And also we switch on the digital pin number 13, where the LED is connected. So this is only for myself to give me an indication that I recognize the button press. This is the first level of troubleshooting which I included for myself. So the first thing, if you write this program, that you want to know is, do I even recognize the button as being pressed or not? If you don't have such a level of troubleshooting and your circuit does not work, you never know, is it because you didn't even notice that the push button or the pedal was pressed? Or is it something with the MIDI protocol, or is it something with your interface logic? So you have a lot of places. If you build a project like this, it's always good to have a little bit more troubleshooting or testing in between levels that help you to make clear that the program works as you intend it to work, or as you think it works. It's not the same. Intention and what it really does is not the same sometimes. So, and here we check if the if the pedal is released, and then we simply undo the sustain. We send again message on message 64 with the value 64, which is the sustain pedal, and 0 is the volume. We switch it off and we send it on channel 1. You can also use other MIDI channels if you want to. Then you have to adjust these numbers here. This will not be 1. You could also use channel 2 or channel 8 or whatever you want. Then you need to adjust the numbers here. And then I switch off the LED. And this pretty much is it. So here you can see the board in action. When I press the pedal, you can see the upper LED, which is the LED connected to pin number 13, will be switched on and off. So this is the first thing that I tested. And then the second thing that I tested, which is also what I would recommend you do, you should connect an oscilloscope to the cable connecting to pin number 1, TX. This is where the MIDI message will be sent, and you will have some pulses going out whenever you press the pedal and release the pedal. And then you can, as a third level of testing, before you connect your MIDI cable to the output of the circuit, which I have described here on the paper, you can also connect an LED. Now what you do, you simulate the internal LED of the optocoupler by connecting an external LED, and you will see it blinking. It will be very short pulses. It will not be very bright because the LED doesn't even get fully turned on. And this gives you an indication that your circuit works. And then the next thing is you can connect it to your keyboard, and you should have no problems getting this to work as well. As I said, you can also use this for other MIDI commands. I used it for the pedal, but you can also use it for volume. You could use it for changing sounds. Everything that can be controlled via MIDI can be controlled with such an interface logic and the program that I have shown you. Of course, you have to modify the program code, sending other MIDI messages and maybe other values depending on what you want to do. So I will now put this little circuit into a plastic box. I will not spend a lot of time because it's only a temporary solution, and I will use duct tape to keep everything in place so it will be safe enough so I can use it on stage for the upcoming concerts. I have now put the little circuit into a little plastic box, secured the cables with a bit of tape. It will be good enough for the upcoming gigs, and I can use my pedal. Now let's end this video with a little demonstration. I hope you liked this video. If you did like it, please come back. There will be more videos about audio electronics, microcontroller circuits. We will also do repairs, and I have some interesting stuff coming, like I want to show you my electronic tuning devices. So if this sounds interesting to you, please come back anytime. And now let's do some little demo of the now working pedal circuit. Nice sustain. Bye for now.